Yes, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the concept of ionization energy, and this is going to be a comparison of the first, second, third, and fourth ionization energy of aluminium. Now, this is going to assist us in trying to understand the various compounds which are going to be formed by these specific elements. And of course, specifically for aluminium, we're going to see that there's going to be a specific trend in which this second, or rather first, second, and third, and even fourth ionization energy are going to be displaying. And this is going to assist us in trying to interpret various reactions which are going to be taking place on aluminum and its compounds. Now, if we try to look at this one, of course, given aluminum's electronic configuration with an atomic number of 13, so we had this one given as aluminium, and then we had this one given as neon, and then we had, of course, we're going to have this given as the 3s orbital, which contained 2 electrons, and then we had the 3p1 orbital given as this. So these are going to be the s and p electrons, which are going to be valence electrons, and therefore this is going to be losing these specific electrons in order to obtain the first, second, third ionization energy given in that specific order with respective values. Now, the first ionization energy is going to be given as 580 kilojoules per mole. And of course, we are going to see that the second ionization energy is going to be considerably large in terms of size. And it is going to be, of course, experienced due to, of course, the positive proton, which is going to be a positive charge in the nucleus, which is, of course, going to be pulling the remaining electrons with a stronger force, and therefore making it difficult for another electron to be taken out of that specific system. Now, this is going to be increasing in this specific trend due to the availability of more positive charge pulling lesser electrons. As each successive electron is being pulled from the system, of course, that is going to be creating more, the ratio of positive charges greater than the negative charges, which is going to be basically the charges of the remaining electron. Now, that's going to lead to a considerable increase in the ionization energy, as we can see from this. So from 580 kilojoules per mole for the first ionization energy, we're going to have the second one at 1815 kilojoules per mole. And of course, the third one is 2740 kilojoules per mole. And the last one is going to be considerably great for the fourth ionization energy. Now, as we can see at this specific point, the valence electrons will have been taken out of the system. And then we're going to see at this particular point, then therefore we are going to be having the stability of a noble gas, which is a neon, having this large quantity of ionization energy being shown as such. Now, in consideration of perhaps the trend across the trend across the specific period, we're going to see that if we consider the second period, we're going to see that there's going to be a specific change, and perhaps I can give that one in terms of an illustration so that we can create a contrast for that one. Now, in contrast from the first description we had for basically the description of energies, ionization energies for the first, second, third, and fourth for aluminium, we're going to look at the group. Basically, this is going to be a period 2 elements of beryllium, boron, carbon, nitrogen, and oxygen. And of course, this is going to be excluding carbon. So we're going to have beryllium, boron, nitrogen, and oxygen of this specific atomic number. Now, I've given their electronic configuration in terms of this specific illustration. And in this particular case, I'm going to request us to be creating emphasis in this specific case. Now, there's going to be a general decrease in the ionization energy across this specific period. And this is going to be realized due to the fact that the electrons in the field of the 2s orbital is going to be finding some shielding effect. Now, as we move down or across this specific period, we're going to see that there's going to be a decrease in ionization energy. So if you look at this specific one, of course, we're going to be having a larger or a particular value, let's say x kilojoules per mole at this specific point. But as we go across the group, we're going to see that there's going to be an addition orbital over the 2p1 orbital being given as this. So in this case, whenever this specific electron is going to be pulled out of the system, this 2s orbital is going to be creating a shielding effect, unlike the first one whereby this specific, of course, electron are going to be pulled from the 2s orbital. Now in this case, the 2p orbital is going to be experiencing some shielding effect of the 2s at the 2s2 orbital, and therefore there's going to be generally less amount of energy required to pull the electron, the 2p1 electron at this specific point out of the system, due to the less amount of energy, attractive energy being experienced from the nucleus given as such. So that's going to explain the trend which we are going to witness across that specific period. And that is going to explain the particular trend in ionization energy which we are going to experience in this particular case. Now for nitrogen and oxygen, we're going to see that the extra electron repulsion in the doubly occupied 2p orbital, of course, are going to be creating some differences in ionization energy. And of course, we are going to see that if we give this specific perhaps representation in terms of the orbital diagram, I'm going to have this one given in this particular case for nitrogen and oxygen for the 2s, the 1s. So for nitrogen, we're going to have the 1s orbital having those two specific electrons being paired in opposite direction as such, and then we're going to have the 2s orbitals having those two electrons as well pairing up as such. And then we shall have the p orbital for the 3 orbitals for the nitrogen and oxygen, of course, being given as such. So for the nitrogen, we're going to have the 3 electrons being given as such. And for oxygen, there's going to be an additional electron which is going to be given as this one. And of course, there's going to be an electron that is going to start pairing at this specific point. So we are going to see that the extra electron repulsion in the doubly occupied the p orbital is going to be, of course, giving us a difference in this ionization energy. In that, we are going to see this specific decrease in ionization energy, especially for this oxygen being shown as this. And of course, this is going to be due to the extra electron that has been added into the system in this specific case. So in case we are going to look at some of the, of course, examples like phosphorus and sulfur, we can give this specific amount of ionization energy for phosphorus and sulfur. These ones are going to be having an atomic number for phosphorus and sulfur, of course, which are going to be having also the same organization of electrons. And therefore, we are going to have the phosphorus ionization energy of 1060 kilojoules per mole, given as such. So that's going to be the first ionization energy for phosphorus. And then we shall have 1005 kilojoules per mole for sulfur. That's going to be the first ionization energy. So in this case, the difference in this first ionization energy is going to be due to an extra electron which has been added into the system, and therefore there's going to be a decrease. So the configuration is going to be analogous to this, whereby one of the orbitals of the p is going to be having an extra electron, and therefore that's going to be explaining the difference in ionization energy as I've given on the board. So kindly check our description boxes for various links of other videos, and we shall be looking at other elements in terms of their ionization energy, so that we are able to appreciate the various characteristics in terms of perhaps the chemical characteristics which we are going to come across in various reactions. So that is it for now, guys. By God bless you. Catch us in our next video.